And we'll get Steve wired up. We have next speaker is Steve Legensky. He's the founder of Intelligent Light and enabling CFD on the web, or on the cloud, sorry. Wherever. We did have a meta center, and then we had grids, and now we have clouds, and it's all the same.
Yeah, what goes around comes around, right? That's what they say, right?
Yep.
What goes around comes around. Hi, everybody. Hopefully this is going to be a little bit different. Intelligent Light is a software provider, and I'm going to talk a little bit about enabling customers to use remote computing resources by solving the data access problem for CFD. So the title of my talk is Revolutionizing Innovation with On-Demand HPC. I have to thank the sponsors for giving me a chance to talk, and also Brian Kuchik for getting me up here to be able to say a few things today. Thank you, Brian. So Intelligent Light's a small company. We were established in 1984, so we've been around 30 years. So that shows you how old I am. And we have our primary software is called FieldView. It's a CFD post-processing suite of tools. We have a global customer base today, providing to all the major aircraft and automotive guys and top Formula One teams, anybody that's basically in the CFD space. What's different about us is we solve problems for people in CFD. We don't sell CFD solver codes. We don't sell mesh generators. Instead, we try to help people get what they are investing in CFD for, which is answers. So helping people do more with less and make better decisions. We have CFD practitioners on staff, and I myself am an electrical engineer. We kind of bridge the three elements here, which is the customer, the CFD vendors, and also the IT providers. And we'll see how HPC and the changes to computing architecture is not only a great opportunity, but has also been creating problems for a lot of people in computational fluid dynamics, or CFD. So our FieldView product started in 1990, as I said. And I have this little background here because this is the major architectural progress of our product, and it's not been driven so much by compute as it is by access to data. So when we first started, for the first 10 years, everything was about visualization and post-processing on a desktop, right? You copied your files to your local machine, and you worked on it, you made a report, sent to your boss. But as compute got farther away, it wasn't possible to always copy things down to your local workstation. So we added a native client-server capability. So the server sits on the HPC resource, and you do your interactive stuff on your desktop. 2004 MPI parallel. We don't really need thousands of processors. We can do 30 billion cells on 256 processors. So we're not like the compute part. Our job is a lot easier on the post-processing side. Those architectures are all connected, right? So you're connected from the desktop to the HPC machine. In 2005, we started to work with this idea of extracts, or indexing, where can we use the HPC resource to pull the important part of the solution out from the big terabytes of data and bring that smaller part to bear to solve the problem. In CFD, typically the engineers are interested in the end of this game in 3% of what's in the file. 97% is there for the physics to solve the problem. But if you're calculating skin drag on something, you only need the surface. All the rest of it is to make the physics happen. So we came up with this idea of extract databases, and many of these things were funded by SBIR research, which we're very grateful for. And so XDBs took away the need for a direct connection to the HPC resource. And I'll get into that later. What we've really been focusing on now since 2013 is in situ extraction of data. Actually instrumenting the solver codes to pull out the important parts while the solver is running on the HPC resource, completely avoiding writing out the big files, and therefore eliminating the big file copying problem. And that's been helped by an SBIR from Department of Energy. We're commercializing Department of Energy's open source visit code. And so we'll talk about the impacts of that later. So just a little background on CFD in the cloud. CFD codes, they're well suited to cloud computing. They parallelize nicely. The input data is usually small. Jobs run for a long time. It's really good stuff. But the results files can be very large, and there can be many files. So you want to analyze those files because that's the stuff you want to get your answers from. But you can upload 100 megabytes and end up with 16 terabytes of results. So that is the problem that's been driving our company to try to help our customers. That's what I'm going to focus on today. And of course, the issues of bandwidth and security, those are problems that have been talked about a lot and probably be talked about tomorrow, but they're serious problems. So I'm going to go through quickly 3 customer examples. ZIPP Speed Weaponry, which makes bike wheels for racing. Daimler, Mercedes-Benz, where we did a multi-continent vehicle thermal management project for them. And DoD Create program, which we've just recently got to start using in situ, doing compute in Maui, taking what they need into very small files and bringing that back to Pax River for analyzing. And with this slide, I like to say both the machine horsepower and speed, as well as the compute horsepower and speed, increases as you go down the slide, from the bicycle to the F-16. So ZIPP is a story of trying to get a small business to use a high-performance computer. They're a designer and producer of the world's most advanced bicycle racing wheels, $1,800 a pop for a wheel. They're the only remaining U.S. manufacturer, and they make them in Indianapolis. And up to recent time, they did all their design by wind tunnel, not CFD, because they didn't want to take the risk on software and HPC and all that stuff. From their perspective, the risk of an investment was prohibitive. It's not the ROI. You don't talk about return until you've gotten over the risk. And so they also are used to using a wind tunnel. When they measure it's 20 pounds of force, they know it's 20 pounds of force. With CFD, they don't know any of that stuff. For the bike wheel stuff, the unsteady effects are very important. And in the world of aerospace and automotive, that's called big CFD. Everybody in those spaces uses a lot of what's called steady state CFD, which is fluid statics, which in the real world doesn't really exist. It's kind of a way to model things that's not really that realistic. So here's a small company that needs the highest end of CFD in order to get started. So they turned to us, and we formed a team between Dell and our systems and CD Adapco to try to find a way to get them going with CFD. So this is a kind of a slide of the typical batch workflow in the cloud. You run the solver, you extract forces and images, and you hope that the images and the forces you extract are what you're looking for. But of course, you'd much rather be able to interact and see how things are going more directly. But what I want to do is go right to the next slide, since my time is short. I mentioned earlier the XDBs. So if you look at the solver statistics, each time step of that bicycle wheel going around is 16 gigabytes of data. So the terabytes for one study. So it takes 2 days to compute that stuff on 32 cores. Using the FieldView post-processing suite, we get down to these XDB files. They're 46 times smaller than the CFD files. And you use the high-performance compute cores to do that extract. So you've already got the cores to do the CFD, use them to do the extract stuff. Bring that down to your workstation, it's completely, the numerical fidelity is exactly the same as though you had the CFD solution at your desktop. So this was to get rid of one of the risks for them, because they immediately saw this as a bottleneck. The results for them, the return on the investment, they came up with a new wheel. They really wanted to try it with CFD. They tried this out, they got 100% category revenue growth, created 120 new US manufacturing jobs, not CFD jobs or HPC jobs, manufacturing jobs. And they're kicking butt in bicycle wheels. So this is a story of getting a small guy to use HPC by solving some of the problems in the way. Now we'll go to a slightly larger organization, Daimler, in Germany. And I wanted to show this picture of this particular car because in Daimler's case, all of their CFD and thermal analysis is done on the CAD data. So they take the data from CAD and throw that bulk into a system that meshes it. They don't have people standing around making custom meshes and all that. They just bulk it right in there. So what happens is you have details down to every bolt. And now this is a German company, right? So you have bolt number 5, bolt number 6. And it's all in the names. And the German names are very long. I mean, I'm not saying anything bad about Germany, but the names are very long, right? So, but within that string is like, is it aluminum? Is it steel? Is it rubber? All the information you need for post-processing is in that name string. But there's a lot of it. There's thousands of parts, dozens of materials. And what they're interested in is, will the car catch on fire? In the auto industry, I see Alex is here from Ford. In the auto industry, there's 2 things that analysis are really important for. Don't catch on fire don't do bad in a crash. That is what's driven the HPC industry since the beginning of Cray. So this is a vehicle thermal analysis example. When Daimler does their work, they compute it near here in Seattle. Their engineering is located in Sindelfingen, Germany. Their computational fluid dynamics partner is in Long Island, and we're located in New Jersey, right by Giants Stadium. So you have these teams all across the place having to exchange data, transferring gigabytes. The solution file, even small extracts is too slow. And the real solution by internet, by FTP, it's just not an option. These are multi-terabyte files. And you have basically two different simulations, a full solid model material simulation for the thermal properties, and then a frozen CFD model for the airflow under the hood and through the car. So we came up with a solution for them, and this was, again, kind of a solution provider thing. They have the expertise to design cars. They don't know really much about data management for CFD. We came up with a scheme that uses FieldView and some Java macros in Adapco to break their giant files down into these small groups. I was mentioned earlier, indexing things. So you have them broken down ahead of time before you move them. Each part of the car is broken into a small file. So if you're a guy that only needs to look at the alternator, you have very small files to work with, and you know them by name. Even though the names are very long German names, you know them by name. And so in this case, we went from 30 gigabytes per time step to 4 gigabytes per time step, which over hundreds of time steps makes a big difference. And in the end, they were able to get plots from this setup that we set for them in 10 days that usually take them 3 months, including shipping disks back and forth and just reading these files. Once you compress things down to be very small, once you extract what you need, just the time to save in reading a file. Disks are getting faster, but they're not that much faster. They'll always be slower than the compute. The compute is making the data problem worse and worse every time. Okay, DoD Create AV. So this is our first successful industrial partner for in situ processing, and I'll talk a little bit about that in detail, because this is the thing I think is very interesting, especially for people who are cloud providers. Because essentially, if you can keep your people from having to write to disk, and write to a database disk, that takes sometimes as long as it takes to compute. That's wasted time. If you can do in situ extraction, you cut that wasted time out. So this is a picture actually of an F-16 with vortex structures on it. And the particular group we're working with is called the Seek Eagle, and their job is to certify aircraft handling with all the different kinds of weapons you can put on them, different kinds of bombs. They have all these different places to stick different kinds of bombs. And this is a story that's been told to me by aerospace guys. We make a nice clean airplane or a nice clean helicopter, and it goes really fast, and it does all these great things. And as soon as the customer gets it, they start hanging all these things on it, and they want to know if it's still going to work. So Seek Eagle's job is to go through all those scenarios. And they actually have a system where you fly
a flight simulator. And that data is what drives the creation of the CFD meshes and parameters. It's amazing stuff. So their stuff is unsteady, it's big. So the unsteady data is computed at Maui, the Maui High Performance Computing Center, which is the great, your tax dollars at work, the Maui High Performance Computer Center that nobody on the mainland can visit. That's how it works out. So if you got a sign there, you're all set. But if you're working in the Pax River, you don't get to go to Maui. So they called us and said, we're generating just too many files. They're too big. We can't do anything. So we supported them integrating Visit, what's called libsim, into Kestrel. And I'm going to try not to use the laser here, but I'll go. Essentially, you take this part of our product, the Visit LiveSim, and you integrate it, you stitch it into the solver. So it does in-memory transfer. So instead of writing out the volume results, you directly extract the stuff from the memory. And we've now added to Visit, the open source Visit, the XDB export. So it's in the 2.8 Visit release. And so you can write these things out and then later bring the much smaller files over to FieldView. And the whole thing about this is, in order for this to work, we decided we have to blend both the open source and the software business. So we don't charge any money or use any licensing for any of our products on the server side. We only have licensing for what you use on. So that's what makes this possible. They can scale to any size, and I don't care. I don't have to generate flexible keys or involved in any stuff. So conclusions, last slide. Companies that have not used HPC and even CFD before can leverage a cloud computing to get started. We heard that from AWS. That's a great thing. But whether you're a beginner or a seasoned expert with HPC, data management is a key problem that the hardware providers are not really going to solve except to say buy bigger and faster disks. Panasas notwithstanding. Okay? And our job is to be able to help our customers, listening to them, and solve these problems so they can get their job done with the resources. So I think I just about made it.
Thank you.